In this lecture, we'll take a look at applying Bernoulli's equation to several examples. So the first example we want to work is example 5.3. So here we have a pipe with water flow. We want to determine the average velocity of the flow in the pipe and both the static and dynamic pressure at point B. So this is an example that we worked through without numbers in the previous lecture. So here in this example, we have a straight tube. We have we're going to look at a datum, a reference point. It's going to be the center of the pipe. So here, we can apply Bernoulli's equations at point A and point B. We're told h of A is 90 millimeters, and we're told h of B is 150 millimeters. So right away, we apply Bernoulli's equations at point A and point B. So we write PA over gamma plus VA squared over 2G plus Z at A equals similar quantities at point B. So here we can, what's the pressure at point A? Well, it's rho G times H, right? So it's the density of water times G times H of A. Gamma, remember, is the density times G. So right away we can cancel out some terms, right? We can cancel these terms out of that side of the equation. The other side of the equation, we have the similar kind of thing for the pressure at B. So we can cancel out this term and those terms. So since we're measuring things from the same reference point, Z at A and Z at B are both going to be 0, so those terms are 0. The velocity at B, this is a stagnation point again, so the velocity there is 0. So we can solve this equation for V at A. So it's the square root of 2G times the height difference. And since we know this is 1.5 meters, I'm sorry, it's 0.150 meters, and this is 0.090 meters. We can plug those in for HA and HB, and we can calculate the velocity at A, which is 1.08 meters per second. We also want to know what the static and dynamic pressure is. So remembering back from the previous lecture, the stagnation pressure is equal to the static pressure plus the dynamic pressure. And since the pressure at A and B are the same, it's just rho G times H of A, which we can calculate, 883 pascals. The dynamic pressure is the density times the velocity squared over 2. So there we can calculate, we know the velocity, we can calculate 589 pascals for the dynamic pressure. So let's take a look at example 5.4. Here we have 3 pounds per second of air flow steadily through this rectangular duct. We want to determine the pressure change that occurs between the ends of the transition. So what happens is here at the entrance, it's 1 feet by 1.5 feet, and at the exit, it's 1.5 feet, but the height changes to 0.5 feet. So it's a different, area at the entrance than the exit. So first, in this kind of equation situation, let's apply the continuity equation first. So here, we want to define our control volume as shown in red. The first term is going to be 0 because we're not making air inside of our control volume. And we'll have the second term to worry about, so we'll have the entrance and exit terms as usual. So we'll have minus VA AA plus VB AB. So in this case, this is QA, this is QB, V times A is Q. So in this case, they're equal. So we can find, we're given what Q is because Q is this m dot divided by the density. So this is our m dot term, 3 pounds per second. We can divide by the density. So we can find our Q is 40 cubic feet per second. So knowing that and knowing these dimensions for the area at A and the area at B, we can find the velocity at the entrance and the velocity at the exit. So now that we have those two known quantities, we can use the Bernoulli's equations to find the information we need. So from the previous slide, we found both the velocity at A and the velocity at B. Let's apply Bernoulli's equation. So at point A, we can write the left-hand term as same as always. Same thing for point B. We just have to plug in the information. Pressure at A, we don't know. We know what the density at A is. Now we know what the velocity at A is. Since we're going to measure along the same center line, same reference point in the middle of our duct, and so the ZA is going to be equal to ZB. Those terms both cancel. We don't know what the pressure at B is, but we know the velocity term. So we end up with the pressure difference between, by solving this for PA minus PB, we find that it's 0.0173 psi. So it's not much difference in pressure from point A to point B. Let's take a look at example 5.5. Here we have a gas tank that contains 6 inches depth of gasoline on top of 2 inches of water. We want to find the time needed to drain the water tank if the drain hole has a diameter of 0.25 inches. The tank is given to be 1.5 feet wide and 3 feet long. The specific weight of gasoline is given, and also for water. So first, let's apply Bernoulli's equation. We apply it between points B and C because that's the area of interest, and it's along a straight line in line with the pipe. So here we we can write both sides of the equation. We know what the pressure at B is because the pressure at B is simply equal to the weight of the gasoline. So the pressure at B is gamma H. So gamma for gasoline times the height. Since gamma's in feet, we'll convert the 6 inches here to feet, 0.5 feet. Multiply this out, we find the pressure at B. So the pressure at B is known. The gamma is known for the water. So B here, remember, it's we use since we're right at the interface, it's the water, so the density of water is what gets used on both sides. The velocity at B is going to be smaller than the velocity at C, so we'll take the velocity at B to be 0. H is, of course, the height here, H. And VC is what we're trying to find. So we have two unknowns. We have H and the velocity at C. So we end up with an equation with two unknowns. So we obviously need another equation. We apply Bernoulli's equation. We have one equation with two unknowns. We have to find another equation to use. So let's look at the continuity equation. So if we apply the continuity equation, so our control volume here is going to be our shaded area in red here, boundary layer. So again, we're not, the first term is 0 because we're not changing anything that we're affecting anything inside the control volume. And again, we end up with things coming into the control volume, things going out of the control volume. So we get the same familiar term we're kind of familiar with. Now this term is easy here for the velocity at C, the area at C. This is just our pi r squared. This is considered to be a cylinder here. But what about at B? Well, it's pretty easy to get the area. That's just 1.5 feet times 3 feet. But here, this height is changing. So this velocity, we'll take it to be the derivative of the height with respect to time. And it's negative because it's decreasing. So you got a negative times a negative makes that a positive. Take all this stuff to the other side, and so you can write this equation as dA, the derivative of h respect to t is equal to this term. And so from the Bernoulli's equation, we found that VC is equal to this, so we can plug that directly in. Let me show you what I'm doing here. I'm taking this term and I'm plugging it in for this value here. So when you do that, you get a differential equation involving just h. So you can do a little simplification. And on the next side, we can actually solve this. because we can, here's our equation from the previous slide. We take the dt over to the other side um, and take the h term on the other side. So simply put all the h terms on one side and the dt on the other side, and we integrate from our initial height, which is 2 inches here, to 0. So remember, everything's in feet here, so we have to convert our lower limit is going to be 2 inches divided by 12 feet to 0, because that starts at time 0, and then how long is it? Time d is going to be the time it takes for all this water to drain out. So if you perform the integration on both sides, you end up with the only unknown, which is the TD, the time to drain. By solving, you can find the time to drain is 6.86 minutes.